everyone. Today we are learning chapter 5, phase equilibrium. Do you guys remember that in STSP 113 we are already learned about phase equilibrium. So for my part, I will make a revision about what is phase diagram, phase rule, and phase. Phase diagram is a graph representation of what equilibrium phases at various temperature, pressure, and composition. Phases is a region in which properties and composition are spatially uniform. This is the example of phase diagram of H2O. For phases is liquid, solid, liquid, and gas. From the phase diagram, we can know the following information. First is phases present in equilibrium. Second, the compositions of phases present at any time during heating or cooling. The fraction of phases present, the range of solid solubility of an element or compound in another. Next, we need to know about this phase rule. From this phase rule, we can know about the degree of freedom in a system. And the formula is F equal to 2 plus C minus P. F is degree of freedom. C is the components. And P is the phases.
Hi, so I'm going to continue what Shuhu has presented before. So as a single phase structure are heated or cooled, they can undergo a number of polymorphic transformation, which is reconstructive transformation and also displaxive transformation. So what is reconstructive transformation? So reconstructive transformation, it involves the breaking and the rearrangement of bonds. The definition is actually an isochemical change in a crystal structure in which chemical bonds are broken and reformed. So it's occurred by nucleation. So what is actually nucleation? Nucleation is a first random formation of distinct thermodynamic new phase that have the ability to grow into large size atom and molecule. So for the example is quartz. Quartz is a crystalline mineral composed of silicon and oxygen atom. So the second one is displacive transformation. It's occurred by the displacement of atomic planes, and the result we will get the heavily twisted. So this is the example of the schematic of displacive transformation and also reconstructive transformation. Hi guys, so next is zirconia. Zirconia is actually made of zirconium, a metal with the same properties as titanium. So in 1 atm pressure, zirconia will go through the following transformation, which is monoclinic, and then after it reaches the temperature at 1170 Celsius, it will go to tetragonal structure, and after that, after it reached 2370 Celsius, it will turn to cubic, and finally after it reaches 2680 Celsius, it will turn into liquid. Hi. So next is barium titanium. When it's undergo a heating processes, it will form rhombohedral structure, and after that it will form orthorhombic structure, and when it reaches 0 Celsius, it will form tetragonal. So when during the 0 Celsius until it reaches 130 Celsius, it will form the cubic. So after more than 130 Celsius, the unit cell is cubic, and titanium's ions are centered in the unit cell. So between the 100 to 130 until 0 Celsius, the barium titanium has a distorted ferrous-clay structure, which is the structure before it reached 130, the thrombohedral, orthorhombic, and also tetragonal. Hi guys, so the next one is silica. So silica has a multitude of polymorphs that undergo a number of both dispersive and reconstructive transformation. So it returns the high quarks into the low quarks. So it's associated with a large volume change. So open cool, it will create large residual strength that will make it lose of strength. So to avoid all the problem, all the quartz is converted into cristobalite. Pause. Oh, banyak sangat lah.
Hello everyone. Okay, today we will continue our chapter 5. One of the syllabus is binary system and solid solution. Okay, so from binary system, it is consists of two components, which are and the number of degree freedom must be F equal to 4 minus P. P is pressure in ATM. Okay, next, there are three factors that will depend the binary system. Three factors are temperature, pressure, and component. So, this component will mix together and will come with three different outcomes, which are first, complete solid solution, which are there are formation of two different elements that are homogeneous, and the second one is partial solid solubility without formation of intermediate phase, and the third one is partial solid solubility with formation of intermediate phase. Next one, we will continue with solid solution. There are two different types of solid solution, which are first interstitial, and the second one is substitutional. Okay, as we learned at STSP 1113, interstitial is other foreigner atoms will enter to the lattice atom, and substitutional is one of the atom will substitute from the actual host. So, interstitial is if the solid atoms is too small, and then the interstitial solution combination will be more easily to be formed. For substitutional, it is a directly substitution between two ions, which are, if cation ion must be with cation ion, if anion it must be with anion. Okay, so the last one is four different factors that will depend complete solid solubility, which are the first one, the structure type. Structure type, there are three: solid, liquid, and gas. It must be same structure type. For example, SiO2 silica is a combination of silica solid and O gas oxygen. So the SiO2 it can be from solid solubility because the structure type is different. So the second one is valence factor. The two ends member of the solute must be the same one. If not, the host can't be neutrality form lah. Okay. The third one is size factor. The size difference between the solute and the solvent must be not more than 15%. So the size difference must be less than 50%. So the last factor for complete solid solubility is the chemical effect. The chemical affinity must be not too high between the two end members.
Hello students. Today we continue to learn about the eutectic diagram with partial solid solubility. So you guys need to know that most ceramic binary phase exhibit partial solubility. If you look here, this is a eutectic phase diagram, and you can see that there are two components in here. The first one is magnesium oxide, and the other one is calcium oxide. And this diagram shows this diagram shows that the vertical line is the represent the temperature and the horizontal line represent the composition in percentage. Alright. Addition of one component to another one component. Addition of one component to another one component will lower the freezing point of the mixture. This will lower the liquidus curve for both ends, which will intersect here at a point. The intersection of this liquidus curve is known as eutectic temperature, or we can say is a eutectic point. Below the eutectic point, the eutectic point shows the lowest temperature which liquid can exist. At eutectic temperature, there are three phases, where we can see here that the eutectic composition of the calcium oxide is at 65%. Just below the eutectic temperature, there are two phases of very different composition. It is L to the solid 1 plus solid 2, or we can say that it is alpha solid plus beta solid. So it's where from the liquid phase it goes straight to the magnesium oxide solid, to the calcium oxide solid, and it gives the calcium. It shows the calcium rich region and magnesium rich region.
Hello guys, my name is Ari and I'm gonna continue the explanation from Farhan, especially about the partial solid solubility. But what is partial solid solubility at first? First, you understand there's a thing called solid solubility, where two components just mix together really well as homogeneous. That is solid solubility. And partial is when they are partially mixed. So it means they are not fully homogeneous. So let's say if you have component AO and also BO, they are only 20% able to mix with each other. So that is what you mean by partial. So what's the main reason of this? Because of the absence of affinity. So this is the keyword. So what does this actually mean? This actually means about the loss of attraction between one compound to one compound. So why is that? That is because when the electronegativity is not strong enough to cause a pull of attraction between both of them, thus this reaction produces an intermediate. So thus intermediate compound exists in this case. So for an example, we're going to say AX, BY, O2. This is an example of the component. So what happened is the component AO with the X as the number of moles and also the oxygen having 1 out of the number of moles, and same goes to the Y for the component BO, and then together they form an AX, BY, O2 as an, of course, an stoichiometric reaction. Now I'm going to explain about the congruently and also incongruently. But what is that? As you can see, partial solid solubility, they melt the compound in two different manners. One is congruently and one is incongruently. But what does congruently and incongruently really means? Actually, congruently means that it has no change of composition. So through the phase diagram, you can see there is no change of composition at the fixed point. Meanwhile, in incongruently, there is. So basically, they are just exactly opposite. For an example, the spinel. Spinel is MgO and Al2O3 reacting together in a phase diagram. They do not have a changing composition through the phase diagram. So what would really be the coincident consequences of the phase diagram is that they tend to have smaller series of simple eutectic phase diagram. That is why it is different. And if you guys can see, look through the image, you guys can see that it's the smallest series of eutectic phase diagram very obviously. So that is the consequences of a congruently melting procedure of a partial solid solubility. Meanwhile, when it comes to incongruently, it's kind of different, it's the exact opposite. But in the reaction that we can look at the phase diagram is different, because you can see that it's actually kind of more complicated. There's no smaller size of eutectic phase diagram, it's more to like a peritectic. But then it is actually more complicated, and it tends to look more mind-boggling compared to the congruently.
Assalamualaikum and very good morning. I will continue on ternary system. So the first ternary phase diagram related the phases. Have three component system, that is BO, MO and AO. It has four variables. The first one is temperature, pressure and composition of two components. The three components are represented by equilateral triangle. It is in 3D. But if the pressure is constant, it will be presented in 3D form. So as we can see here, the thicker line is the boundary curves. The boundary curves represent equilibrium between two solid and liquid. The intersection of the boundary curves represent four phases in equilibrium, three solid phases and a liquid. This point is the lowest T at which can exist ternary eutectic. So as you can see here, the temperature will decrease towards the center of the diagram. The temperature will increase here and it will increase from here to here. So at the center of the diagram, the temperature is at the lowest. And any composition of all these curves will crystallize the two faces on either side of the curve. Okay, so we continue to polymorphic transformation in unary system. Okay, so it is a congruent melting of a compound, and as you can see here, the T dependence of the free energy function for the liquid is, this is for the liquid, GT liquid equal to HT liquid minus TS liquid, and for the solid, GT solid minus HT solid equal to HT solid minus TS solid. For H is the enthalpy and S is the entropy. Okay, so free energy changes as T is lowered below the equilibrium temperature, that is Tm. This is the diagram of the free energy. And this is the intersection. The intersection marks the Tm, that is the melting temperature. So the heat capacities are not cross function of T. The T range considered is not too large. Okay, so the GT liquid is deeper than GT solid because entropy content of the liquid is larger than that of the solid. On the T is greater than Tm, the line intersects the liquid has the lowest energy. In this phase, the liquid has the lowest energy and there is more stable phase. But if the T is lower than the Tm, here, the solid has the lower energy, therefore the solid has a more stable phase. Intersection of the T, as I said before, is the melting point of the solid.
Assalamualaikum warahmatullahi wabarakatuh. I'm Muhammad Ibrahim Makruzi. Okay, today I want to explain about documentary and non-documentary compound. What is documentary and non-documentary compound? Documentary compound is compound that they maintain their ratio as they will form despite having defects in them. Having defects is the meaning of having defects is non-stable of compound, such as Fe, such as sorry, I forgot. Okay, but it means non-stable compound. It can react with any time and any other element. So, non-stoichiometric compound is a compound that chemical compound, almost always solid inorganic compound, and it's better to be known that it's non-stable compound. Okay, as we look free energy and composition diagram. As we look here, how we can know the compound in this diagram. Here is the stoichiometric compound. This consists of stoichiometric compound, and this non-stoichiometric, this stoichiometric. Here, when stoichiometric compound having a reaction, it's become non-stoichiometric, and it's here, this is non-stoichiometric, and then become the stoichiometric compound again. How can we know the compound in the free diagram, in the free energy and composition diagram? The reaction take over here, and when the reaction come to the end, it exists. Compound exists at range of stability. New compound, it exists here. So when we look at the diagram, when we look here, we will know the compound of the diagram.
Sure. Okay guys, we just ended chapter 5. So I just want to ask whether you guys have any question you guys want to ask me. Yes, sure.
What is meant by free energy of system is lowest?
Okay, when it comes to free energy, it's basically mean that the energy of the system is very low. And what does that really mean in a practical term? It means that the whole system is in the most stable form. That's what it means by free energy to be the lowest. The next, any other questions?
Okay, the question is, what is the relationship between free energy and phase diagram?
Okay, that is actually a very good question. We have to understand that phase diagram is about composition in variables such as temperature and pressure. And what is that to do with the free energy, right? So actually basically gives free energy tells about the stability of each composition at a fixed percentage and at which level it is the most stable. So that's why it's very important to relate gives free energy and also the phase diagram, because then we can know at which temperature, at which composition, at which variable it is the most stable and the most possible outcome of the product.
Thank you.
Alright.
I want to ask,
Yes,
what
Mani?
is the difference between congruent and incongruent method?
Okay. Basically, in intermediate phase, they are congruent and also incongruent melting. So what does that really mean? It's actually very simple. Congruent melting is when it melts with a fixed composition, while the incongruent has not a fixed composition, as the exact opposite. But then it has a more specific result, which that when it comes to congruent, there is series of smaller steps of mutating if you look at the diagram. But in the opposite of incongruently, you will understand there is a more complicated kind of series when it comes to the phase diagram. Does that answer your question, Mani?
Yes.
Thank you.
I have the last question. What is the difference between reconstructive and displacive transformation?
I see. That's actually a very simple question. Basically, the crystal structure or the crystal arrangement of the compound will have a bonding with each other, and this bonding.
That's all from us.
Thank you.
Kinetic energy of the movement of the crystal, you'll understand they will start to move and form in a different structure. These are called polymorph. So what really meant by reconstructive, and also what was the another one?
Displacive.
Okay, displacive. So when it comes to reconstructive, is when the bonds are broken and rearranged. So that is something that you guys can see through the crystal structure. But then if you look at displacive, basically they do not break the bond, but they will still have different movement. So basically the angle between the bonds might get smaller or even bigger, but it won't break the bond. So that's all the difference between reconstructive and replacative.
Thank you.
Okay, welcome.